to look at another type of optimization problem here today. The difference in the optimization question we're looking at here today is that we will have what are called constraints attached to the problem. And I want to put an example up here on the board because I think it'll be easier than for me trying to explain the theory behind it. Let's just look at a specific example. I can point out some things here. Okay. We'll pick a really simple one to start with. We're going to look at the function 2 times x times y. And the constraint that we have is that x plus y has to equal 12. Okay. All right, this is similar to, we did problems like this in 2 dimensions. But the only difference in 2 dimensions, of course, we didn't have as many variables as we have in this situation. Okay, can we apply the same idea into 3 dimensions? And the answer is yes. Now, before we look at the nice, efficient calculus way to solve these problems, I just want to make sure that everybody understands what's going on behind the scenes. Here's the goal that we're trying to do. We have a constraint that x plus y has to equal 12. So we have to make sure that whatever x's and y's we choose, that they sum up to be 12. Okay? And what we are looking for is we are looking for, in this case, let's just go ahead and say that we want the maximum. Okay? Let's say that we want the maximum value that we can ever get when we multiply 2 times the x coordinate times the y coordinate. But the constraint or the condition, we have to make sure they add up to 12. So let's just start picking some examples and looking at this. Okay? So I'm going to make a little table. I got x, y, and then I've got f over here. Okay? All right, what are some possible combinations of numbers that add up to 12? Well, just give me one of them and let's try it. 6 and 6. Okay, so we'll start with 6 and 6. Okay, definitely it satisfies the constraint. Now I just need to figure out, well, what's the value in the function f? So if I take 2 times 6 times 6, 36, 36 times 2 would be 72. All right, so I get a value of 72. And we've got to decide, is that the biggest value that we can come up with, or is there another combination of numbers that would be bigger? Okay, well, let's pick another number. What's another group of numbers that fit our constraint? Okay? 8 and 4. If we sub in 8 and 4 into our optimization equation, 2 times 8 times 4. 64. Okay, so not quite as big. Okay, so definitely 8 and 4 will not be our answer. And basically what it comes down to is we just keep trying values here, and we're just trying to beat this 72. Can we come up with any other combination of numbers that will beat 72 in terms of a product? Okay, well, let's just try one more. Let's try one where we've got a really big and a really small x and y here. Okay, so maybe 1 times 11. Okay, or we can even do decimals. We could do 0.1 and 11.9. Okay, we can choose these as arbitrarily as we want. Okay, if I just do 1 and 11, though, what do I get for an answer? Well, only 22. So this looks like this is actually getting worse. When we start to spread the x and y apart, it looks like we're getting lower and lower numbers instead of bigger and bigger numbers. So it appears that maybe the best scenario that we've got is the 6 and the 6. Okay? Now, when the problems get more difficult, and even a better question, though, is what do we do to convince ourselves or to kind of prove that 6 and 6 is maybe the best scenario? Or how do we verify that it really is? Okay? Well, it took mathematicians a little while to figure this out, but there was a mathematician named Lagrange who figured out a way of solving these types of problems, and that's the method that I'm going to show you today. The name of the method is called using Lagrange multipliers to solve these optimization problems. Okay? And so we're going to be using this process trying to solve situations like this, where we've got a constraint on a situation. Okay? All right. There's lots of steps to the Lagrange process here, and so I want to kind of go through them one at a time here. Okay? Process number 1, and I'm going to try to use the same language that this particular book uses here, is that they say take the constraint equation and set it equal to 0. That's always our first step. Okay? And so I have to look at my constraint equation, and this is not a bad constraint equation, but I always want to move everything over to one side and set it equal to 0. Okay? So I'm going to subtract that 12 over to the left side, and so for our problem, the constraint equation equal to 0 is this, x plus y minus 12. Okay? All right, step 2 is to, what they say, form the Lagrange function. Okay? The Lagrange function is basically what it does is it combines these two equations together into one equation that we will be able to take derivatives of here in a little bit. The Lagrange equation looks like this. Okay? You always take what's called your optimization equation. Okay? That's kind of the first piece of the Lagrange function. Okay? And then, I need to see how this, I think they use minus in this book here. Yeah. Okay? Minus, and I'll explain what this is here in a second. Okay? Minus lambda times the constraint equation. And that's what they're going to call the Lagrange function. Now, this is just a Greek letter. We wouldn't necessarily have to use lambda. We could just use another English letter. We could use W if we want to. Okay? But that's the symbol that's most commonly used when people talk about Lagrange functions. Okay? So we're going to take our optimization equation minus some variable times our constraint equation. That's how we set up this Lagrange function. So let's do that with our situation. Okay? My optimization equation, the one I'm trying to maximize is 2xy. So I just write down here for optimization, I write 2xy. Okay? Minus lambda times the constraint equation. And the constraint equation that I'm talking about is the one up here in number 1, the one that is equal to 0. That's why they had you move everything over to one side so that we can write this as x plus y minus 12. That's how we get the 12 into the problem. Okay? All right. And so this is what we call the Lagrange function. Okay? And this is the first two steps. Constraint to 0 and then form this function. Okay, now, once we form the function, how did we find maximums and minimums? What did we just do last time? In calculus, we take the derivative and we set the derivative equal to 0. Okay? Well, in this part, very similar. We want to be able to take the derivatives of all these functions and set them equal to 0. Okay? Now, here's the thing. This function, this Lagrange function, has how many variables in it now? Okay, it's got 3. It's got x variable, it's got y variable, and it's now got this new lambda variable in it. Right. So this has 3 variables. So we will need to take 3 partial derivatives. Okay? All right. So let's start over here to the side. What if I take the partial derivative of this function with respect to x? So I want x to be the variable. Okay? Well, what's the derivative of this piece? 2y. Right. Okay? All right. Now, I'm going to go ahead and I think this may help, is even in this step here, let me go ahead and distribute that lambda through. Let's do the little distributive property, and then I think the derivatives will be a little easier for you to see. Okay, you can kind of distribute that through. Some of you may not need to do that. You might just be able to do this derivative without distributing through. Okay, but if I go ahead and distribute through, okay, my derivative here is 2y. What's my derivative here? With respect to x. Negative lambda, right. Okay, so this is 2y minus lambda. The derivative of this with respect to x, 0. And derivative of this, 0. Right? Okay, because there's no x's in them. All right, so I just get 2y minus lambda. Okay, and eventually I'll need to set that equal to 0. All right, what about the partial with respect to y? Okay, what's the derivative of this with respect to y? 2x. The derivative of this with y, 0. This one, negative lambda. And again, the derivative of 12 is 0, so I'm just 2x minus lambda this time. Okay? What is the derivative with respect to lambda? Okay, the derivative of this, 0, because there's no lambdas in it. Derivative of this, negative x. Derivative of this, negative y. And I don't know if anybody's noticed my mistake. I forgot to do something a little bit ago. When I was distributing this through, what should be on here? Should be a 12 lambda, right? I forgot to write down the distribution of lambda through there, okay? So that's really a 12 lambda there. And so the derivative of this with respect to lambda is what? 12, right. Okay. All right, you will notice this, okay? How does this equation, the derivative with respect to lambda, how does that compare to this one right here? It's the exact opposite, and that will always happen. Whenever you take the derivative with respect to lambda, this equation is just always going to be the opposite, and the only reason is because we got this minus sign here in the middle. Okay? So that's always an easy one, a derivative to take. Now, our goal is to set all of these equal to 0 and find out what are the values of x, y, and lambda that make all three of these equations work at the same time. Okay, now that sounds confusing, but it's actually not as difficult or as daunting of a task as it appears. Okay? What we usually try to do is I usually ignore this equation if I can, and I try to solve the first two equations by solving for lambda. Okay? So here's what I mean. If I was to add lambda over to the right side, I would get lambda equals 2y. And if I add lambda over to the right on this one, I would get lambda equals 2x. Okay? I usually try to solve both of these for lambda because if they both equal lambda, what has to be true about these two things? They have to equal each other, don't they? Okay? If this equals if lambda's 10, just to make up a number, if this equals 10 and this equals 10, well then these two things also have to equal each other. And that's usually the process that I go through to try to eliminate a variable. Okay? And so these two things together generate 2y equals 2x, and then if I divide off a 2 from both sides, I see what? Well, I see that y must equal x. Okay? Now, in our situation, if we just stopped at that point and thought about the problem, okay, if we go back to our initial constraint, if x and y are the same number, they both have to be what? They both have to be 6, and that would be the end of the problem. Okay? Now, if you don't get quite this nice of a situation, what you would do at this point, now that y has to equal x, I could come down into this constraint equation, and let's just say, for example, if y is the same thing as x, I could replace this y with an x. And then I continue to solve this equation, and I would end up with just a nice little algebra problem where x turns into 6. Okay? So if it doesn't work out as nicely as this one, then you just substitute that value back in, and then you do a little algebra and solve. To me, that method of solving works pretty well with these Lagrange functions. Try to set the first two functions equal to lambda and come up with something from there. Sometimes you'll get an answer like you'll get y equals 2. Okay, you might actually get a numerical answer. Other times you might get something like y equals x, and then you just take that and then go ahead and utilize that third equation, and usually this method works pretty well. Okay? So what we have found out is through the method of Lagrange multipliers, the best scenario that we can come up with is if x and y are both 6. Okay? It's kind of a proof that this is the one that will produce the maximum value for our situation, and we kind of thought that that might be the case here. Okay? All right, any questions with that example? All right. I'll leave some of this up here. I'll leave kind of the rules up here, and I'll just erase the work for this problem. Then we'll try to do another example here. Okay. Okay, constraint equation goes away, this goes away, and the table goes away. All right. Let's look at the next example here. What if we want to look at this one? Oops. Again, we're trying to maximize a situation. Let's say that we want the maximum of 4xy squared. And the condition this time, the constraint, is that 3x minus 2y has to equal 5. Okay? So a little harder to come up with values this time than the previous time. Okay? But again, let's start out with a table, and let's just see if we can stumble across what we think might be the correct answer. And then we'll use Lagrange multipliers to make sure that we've got the right answer here. Okay? All right, first question, and it's a little bit harder to do this time, but we need to find some ordered pairs that actually fit into this constraint. Okay? Anybody see a nice xy ordered pair that would fit into this constraint? 3 and 2 is a good ordered pair. Because if I sub in 3 for x, that's 9. If I sub in 2 here, that's 4. 9 minus 4 is definitely 5. Okay, so let's go ahead and try it. If I have 3 and 2 here, and I sub those numbers back into my function f, what value do I come up with? Okay, well, x is 3, so that would be 12. 2 squared would be 4. 12 times 4 would be 48. Okay, so we came up with a value of 48. So right now, 48 is the value to beat. Can we come up with something that gives a larger value than 48? Okay, all right, we need to come up with another xy ordered pair. You come up with another possibility. Five and 5 is another good ordered pair. Okay, definitely 15 minus 10 is equal to 5. And so now if we sub in 5 for x and 5 for y, multiply it by 4, this is going to be a lot bigger answer here. What is it? How much? 500. Okay. So definitely this is a better scenario. Now, just as we look at this in general here, as we look at the equation we're trying to maximize in this problem, which do you think we want to be bigger? Do we want bigger x's or bigger y's? Bigger y's. And why would we want bigger y's here? Well, because when we're trying to get a maximum value, we end up squaring the y. That's going to have a bigger impact if we square it. So our goal probably as we're trying to pick these out, our goal is going to be probably try to pick as big of a y coordinate as we can. Now, the thing is, though, the way that this problem is set up, and that's why I had to look at it twice because I wasn't sure that I had copied everything right. If I get a bigger y value, that means I'm subtracting a bigger number. What's that going to mean in terms of x? Isn't x also going to have to continually get bigger? Yeah, if I'm going to be able to subtract a larger number and get 5, that means this has to be subtracting from a larger number. So yeah, x is going to also get bigger. So that's why I questioned this problem and the fact that it appears that I can just keep making these numbers bigger and bigger indefinitely, and I will continue to get bigger and bigger answers here. Okay? But let's go ahead and let's use Lagrange multipliers. Let's see what happens here. I think this might be a little typo in the book. Maybe this was supposed to be a plus sign because this question appears like we can just pick as big a numbers as we want and it'll just continue on forever. We'll just keep getting bigger and bigger products at the end. Okay? But let's go ahead and solve it and let's see what happens. Okay, I want to set the constraint equal to 0. Okay, so that basically means subtract the 5 over. So 3x minus 2y minus 5 goes to 0. Okay, now I've formed the Lagrange function. Okay, I take my optimization equation, 4xy squared, and I subtract lambda times what I just did in step number 1. And we call this equation usually fxy lambda. Okay. All right, now once we have the function set up, now we start doing the derivative work. All right, and again, if you want to, if it's helpful, you can go ahead and distribute that lambda through this equation. Whoops, I want to distribute it through. Okay, so 3x lambda minus 2y lambda and then a plus 5 lambda. If you need to go ahead and distribute that through to help you with derivatives, go ahead. Okay. All right, what is fx on this problem here? Derivative with respect to x. A 4 and a y squared, right, because x is the variable, so everything else is constant. So 4y squared. Derivative with respect to x. Minus 3 lambda. Okay, and then there's no other x's, so there's no more derivative. Okay, derivative with respect to y. Okay, derivative with respect to y on this one. Okay, definitely the 4x is constant, so it will stay there. And then what's the derivative of y squared? 2y. So I have a 4x and then a 2y. Okay, so if we put it all together, it would be 8xy. Okay, all right, this one doesn't have a y. This one does, so its derivative is what? Yep, minus 2 times lambda, and then again no y on the last one. Okay, derivative with respect to lambda. 0.
Shouldn't it be a positive 2y lambda?
Yes, it is. Thank you. Okay. Again, I just made a mistake on my distributive property here. Negative and negative is positive. And so then this should be a positive 2 lambda. Yeah, thank you. Okay. All right, derivative with respect to lambda. From here we get what? Negative 3x. From the next piece, positive 2y. And from the last piece, positive 5. Good. Okay. And like I said, this is your clue. You know, this is probably where I would have noticed the mistake had you not caught it earlier, is that this equation should be the opposite of this one, and I probably would have noticed the sign difference there. Okay? Yeah, but that's good. All right, we want to set all these equal to 0. And my method before is not the only way to solve this, but like I said, I think it's the most efficient. I think it works the best. If we can try to set both of these equations, solve them both for lambda, and then try to get some result from that. Okay? So what I'm going to do is I'm going to add that 3 lambda over to the right side, and then I'm going to divide by 3. I'm going to just go ahead and do all the solving for lambda. I want to do the same thing with the second equation. Okay? 8xy equals negative 2 lambda. I subtract the 2 lambda over, and then I divide off the negative 2. So it'll be negative 4xy equals lambda. I try to solve the first 2 equations for lambda, because then what can I do with these 2 equations? Since they both equal the same thing, they have to equal each other. Right. Okay? And so now I take 4 thirds y squared equals negative 4xy. I just set those 2 equations equal to each other. That's one way of eliminating a variable when you've got this many variables. Okay, now I want to try to solve this and come up with some solution. I want to try to come up with some resolution here. Okay, I see I could divide off a 4 from both sides because the 4 is in the numerator over here, so I can divide that off and it goes away. Okay. Let me go ahead and just add everything over to one side, though. I think this will make more sense for you. Okay, the 4 goes away, so all I have left is xy now, don't I? Okay. Now, what could be factored out of this thing? Okay, I can definitely take out the y, and then what's left is 1/3 y plus x equals 0. So what's one of my possible solutions here? Y equals 0. Okay, now I want to talk about that one first, and then we'll come back and we'll look at the other one here. Okay, if y is equal to 0, what's my product going to be up here? It'll just be 0. Okay, now Lagrange functions are smart, but they're not this smart. Okay, it gave us a solution of 0, but what solution was that? Was that the maximum solution? No, what was it? It's the minimum solution, right? Lagrange functions don't know if it's a maximum solution or a minimum solution, so it just goes ahead and finds them for you, and then you have to make that decision. Well, in this case, we can pretty quickly tell that that's going to be the minimum value. Okay? So that's not the one that we want. The one that we want is this one over here. Okay, and I'll bring that up here so we can see it. 1/3 y plus x has to equal 0. That's the other factor that we think might be giving us this best type answer scenario here. Okay, if I subtract this 1/3 y from both sides, I can get x equals negative 1/3 y. I solve for one of the 2 letters. You can solve for x or y, it doesn't really matter. Okay, and the reason I want to solve for x or y is because now I can take that value and I can sub it back into this third equation. I really haven't used the third equation yet. Okay? All right, so I have negative 3, negative 1/3 y, plus 2y, plus 5 equals 0. Okay? And then we need to solve this for y. Okay? This all turns into a what? Positive 1, right. Okay, so this is just y plus 2y, so that's 3y. Okay, this was 1 and this was 2, so that's how I got the 3 real quick. If I subtract 5 and divide by 3, according to the Lagrange function, the best scenario is if we let y equal negative 5/3. Okay? And if y is negative 5/3, then x must be what? Okay, well, I'll probably just sub it right back into this right here. Okay, so negative 1/3 times negative 5/3 looks like 5/9. as our value of x. Okay? So I'm curious about this. I want to try this out, okay, because I'm not convinced that this really may be our best scenario here. Okay? If x is 5 over 9, and if y is negative 5 over 3, okay, I'll need a little help with this one. What value do we come up with in terms of this situation? So 4 times 5 over 9, and then we've got that 5/3 squared in there. What value does it come up with? 6.17, okay. And we can definitely see that 6.17 is not nearly as big as some of these other questions, or some of these other z values over here, these function values. And so the question then comes up, what happened here? Why did Lagrange tell us that this is the correct answer for this problem when we can clearly see that there are some other values much bigger than that? Okay? Here's my scenario, here's my explanation why. Okay, is that if we were to actually graph this function, this 4xy squared, okay, and then we were to come in and impose this particular constraint on the function, okay, and it's a little bit hard to demonstrate without a nice graphing software, but I'll kind of give you the theory behind it here, okay, what we would find out is that some of these points wouldn't actually show up on the graph. They would be outside of the graph that we would be looking at in this situation, okay? And so, it's kind of, it's not really outside the domain, but that's kind of what it would show up as. This graph actually goes on forever, okay? But if we just look at this individual part of the graph, well, let me give you a different example here. If just say the board, say this whiteboard here is our constraint, okay, or our working surface. I could draw a line on this board, and I could let this line go on forever, right? Okay? So I can be picking ordered pairs way up here off the board and points way below the board. Okay? That's what these would be. Okay? But if I just look at the constraint that I have, or the function that I'm looking at, if this is the whiteboard, okay, there's only certain values on that graph that I can choose, and apparently these were 2 of the values that were off the board. Okay? And so if we just look at the ones that are on the surface that we actually have graphed here, this is the one that gives the largest value in that setting. That's what's really going on behind the screen, behind the scenes. Okay? And so that's why we use this Lagrange method, because it actually helps solve for those scenarios for us. We don't have to decide if these functions are actually on the board or off the board. Okay? All right, so there's another example here. Okay. I think we've got time to work through at least one more here. So let's pick another one. In fact, I might put it up on the screen here as well. Zoom in here a little bit. We'll do this one right here. Oops, too far. There we go. Okay, I'll go ahead and make some room on the board here. I'll let you go ahead and read the problem. So we want to build a fence against a large building so that the fencing material is used on only 3 of the sides of the building. Material for the ends is $8 a foot. Material for the side opposite the building is $6 a foot. Find the dimensions of the yard maximum area that can be enclosed for $1,200. Okay? All right. within word problems, the thing that's different is that we have to pick out the function we're trying to optimize from the word problem, and we have to pick out the constraint from the word problem. Okay? All right. What are we trying to maximize or minimize here? Area. Very last sentence, find the dimensions of the yard of maximum area. So that tells me that I want to write some type of an area equation. Whoops, this marker's about dead. Okay. So instead of calling it F, I'll call it A, just to remind us that we're writing an area function here. Okay? All right, and what shape are we working with here? Doesn't really say in here, but they kind of imply that it's at least a rectangular shape. Okay? They really should say that here, but to me it sounds like, you know, material for the ends costs $8 a foot for the side opposite the building. So it sounds to me like it's rectangular. So let's just go ahead and do rectangular, because I think that's what they're implying here. Okay? So what's the function for area of a rectangle if we know that x and y are the sides? Just x times y, sure. Okay? So the optimization equation is just a really simple x times y. Okay, now the constraint is going to be a little more difficult. All right, and let me draw a picture off to the side here. All right, here's the building up here, so we don't need anything on that side. We'll go ahead and call this x, and we'll go ahead and call this y, just so we have our dimensions all, that everybody labels them the same way here. All right, what's the constraint that we have here? What's the thing that we cannot go above and beyond? The cost of $1,200, right, that's our constraint. And that's a very common constraint in a lot of applications. You only have a certain amount of money to use on this project. So our constraint equation will have a 1,200 equals something in it. Okay, now what are the costs that we have on this one? $8 per foot on the end here, okay? So this side's going to cost me $8 per foot. This side's going to cost me $8 per foot. Okay, so this side will be an 8x, this side will be another 8x. So to me it sounds like 16x. Okay, because 8, you know, however long this side is, we got to multiply it by 8, so 8x. And then this is another 8x. All right, what's the rest of the constraint then? Plus 6y, because we only have one side at $6. Sure. Okay. Okay, now, again, as I was mentioning before, there are lots of possible values that could work in this XY situation, but we've got to look at the constraint itself and the fact that we can't just pick as large of x's and y's as we want, because, you know, we're going to end up going above $1,200. Okay? So what's the Lagrange process tell us to do at this stage? Well, it says go ahead and set this equation equal to 0. So let's do that. Okay, 1,200 minus 16y, or 16x minus 6y equals 0. And then we want to form the Lagrange function. Okay, so the optimization is xy. The lambda times constraint is this. Okay, and I will tell you, if you subtracted the 1,200 over and set it equal to 0, then your equation will just look the opposite of mine, but that won't matter. Eventually, it works out either way. Okay. All right, now, just again, thinking about this problem before we actually start solving this, taking all the derivatives and so forth, where do you think we want to put most of our money in this problem? Do we want to put most of our money on the sides or most of our money on the bottom? As you look at the cost of those, where do we probably want to try to get a bigger value, for x or a bigger value for y? I would say probably we want to try to get a bigger value for y. Okay? And the reason is just because it costs only $6 compared to $8 on the other. Okay? So my guess is, and this may not work out because we have some constraints in here, okay? But my guess is we'll probably have a little bit bigger value for y than we do for x, just on account of the cost. Now, we can't get too big of a value for y, because if we get a really, really big value for y, then we're not going to have very much left over for x. You know, this isn't going to be a very big rectangle for us. Okay, so we've got to try to figure out how big can we make that y so that we still get a decent size area, but yet we keep our costs down as low as possible. Okay, that's what this question's asking. All right, so let's go ahead and work through this here. I'll actually move over to this side because I put the screen down here. Okay, I don't think we need this anymore. All right, what is fx from this Lagrange function? Derivative with respect to x for this. It's just y. Okay, and we'll kind of do this in our head this time. Okay, if I distribute that through, the derivative with respect to x, 0. If I distribute this through, the derivative with respect to x, 16 lambda, right. And if I do the last distributive property, 0. Okay, so that's fx. All right, fy. Okay, derivative of this with respect to y, x. Derivative of this with respect to y, 0. With this with respect to y, 0. And this would, okay, this negative and this negative, so positive 6 lambda, right? Okay. And like I said, if this is losing you here, go ahead and distribute it through, and then it's just easier to see it. Okay, f sub lambda, okay, derivative with respect to lambda. This is 0. This is negative 1200. Next, plus 16x, and then finally plus 6y, right? Just the opposite of the constraint equation is the easiest way. You know, when I was telling you those answers, I'll admit it here, I was just looking at this equation and taking that, switching all the signs. Okay? All right. We set these all equal to 0. I would recommend working with the first two and trying to eliminate the lambda first. Okay? All right, so y equals negative 16 lambda, and x equals negative 6 times lambda. Okay? And then I could just solve for both of these. You know, I could divide off this negative 16 and divide off the negative 6, and I can solve it this way. Okay? Okay? Now those two equations have to equal each other, so y over negative 16 equals x over negative 6. And what would you do at this stage if you were trying to solve this? What algebra technique would we use at this stage? Probably cross multiply, right? Try to eliminate those denominators here. Okay, so negative 6y equals negative 16x when I cross multiply. And now I just need to solve for one of these two. And it doesn't really matter. I'll just go ahead and divide off the negative 6. Negative over negative is positive, so I get 16 divided by 6 times x equals the y value. Notice I didn't get a definitive answer. I didn't get y equals 2 or anything. But this is still very helpful because now I can take this and I can sub it into that constraint equation because I now have a specific thing that I have a specific relationship between x and y that has to be fixed or that has to be met. Okay? So now I come over here, I've got negative 1200 plus 16x plus 6 times 16 over 6x has to equal 0. Now I've reduced it all back to just one variable, and in fact it's even nice because the 6's cancel off here. So 16x plus 16x is 32x. And I'll just do some quick algebra here. What's 1200 divided by 32? Somebody with a calculator can help me out here. Right? Okay, just to make sure I heard you right. All right, so x is 37.5. And then I could quickly get the y by subbing 37.5 into this equation. And what is the value for the y here? 16 over 6 times 37.5. Again, a little help here. Even 100? Okay. All right. So apparently the best scenario for us is to make that rectangle where the y value or the bottom length was 100, and then the sides are 37.5. And is that kind of what we thought would happen? Did we kind of expect that the y would be a lot bigger than the x's? And just in terms of the cost, yeah, that makes sense. Okay? Now, how much bigger was it? Well, whatever 16 over 6 is, if we divided that out, it would tell us how much longer it should be than the other side. Okay, so apparently this is our best scenario. Be careful when you're answering your homework questions because they may not just ask for the x and the y. They may actually ask for the area itself. They may say, what is the maximum area? And I think that's exactly, this one said find the dimensions. And so that's all we really needed was the x and the y. Okay? Now, one more thing I'll point out before you take off here. This may not have been the most efficient way to solve this particular setup. When I got down to this point of x and y equaled something, okay, what I could have done was I could have subbed that in for y, and I could have subbed that in for x, and wouldn't that have changed this whole equation back into lambdas? And then I wouldn't have had any of these fractions down here, and that would have been another way to solve this. Okay? So there are more than one way to solve these equations. If you get stuck trying one way, maybe try to solve for a different variable, and then you might still be able to get the right answer. Okay? All right, we'll see you next time.